Hello everyone. We will be discussing group elements now, though these are very basic units, but in the exam definitely you will be getting some questions. They will be asking you what are the trends, right? Suppose if I begin with S block elements, in S block elements if I take some lithium or sodium, they may ask you which hydroxide is more basic, or which hydride is more reactive, or which chlorate or perchlorate is more reactive or more stable. All such questions can be expected, right? So in this class I will be beginning with S block elements. These are very basic units. They will also be completed very fast, but the only thing that you have to remember is the trends. What are the trends? Either it will be a physical property or some chemical reaction. Okay, so let us begin with S block elements. What are S block elements? All these basics I have explained you in the periodic table in the beginning introductory classes, but just we will have a small revision of all these points. S block elements means these are those elements where the differentiating or the last electron enters into S orbital. So supposing if I take sp df orbitals, the last electron, which we call it as a differentiating electron, that differentiating electron will enter into S orbital, and therefore we call it as S block elements. Altogether how many of these groups are present? Suppose if I choose periodic table, in the periodic table we have different blocks. We call it as S block, P block, D block and F block. Whenever I choose S block, we have only two groups of it, and the group numbering start from S block itself. So the group number will be 1 and 2. Okay, I will give you the points. Altogether S block elements means altogether there are two groups. We call it as group 1 and group 2. There are also other names for it. We simply call them as group 1A and group 2A. 1A are also called as alkali metals. 2A are called as alkaline earth metals. So we are calling them as alkali metals or alkaline earth metals. Simply it concludes that whether it is 1A or 2A, all of them are metals, purely metals. You don't find any non-metals or metalloids. Okay. Coming to the general electronic configuration, the general electronic configuration for all the elements of S block is NS. It is NS1. N is with shell, that depends on the period. It could be 2, 3, 4, 5, 6 or 7. Okay. So just begin with some basics, write down a few points, then I will give you the electronic configurations and the physical and chemical properties. The elements in which the differentiating electron enters into S orbital, are called as S block elements. There are two groups in this block. They are group 1 and group 2. Group 1 and group 2. Next, group 1 is also called as 1A Roman letter. Group 1 is also called as 1A, group 1 or group 1A or alkali metals. Alkali metals. Group 2 is also called as Group 2A, or alkaline earth metals. Alkaline earth metals. Next, all S block elements are metals. All S block elements are metals. Then you just put a separate heading as Group 1A or alkali metals. Today we will begin with Group 1A or alkali metals. Group 1A or alkali metals. The general electronic configuration is NS1. The elements are you can take down the elements: lithium, sodium, potassium, rubidium, cesium and francium. We are not considering hydrogen because it is unjustified. Its position is unjustified, so we begin with lithium, sodium, potassium, rubidium, cesium and francium. You can write down their electronic configurations. Out of all these elements, francium is radioactive. Since francium is radioactive, we need not study about francium and its trends. So we always study the trends starting from lithium up till cesium only. Francium we are not going to study. After writing the electronic configuration, you can simply add that statement. First you write down the configuration, I will give you that statement. Finished? Write a statement. Francium is radioactive. Francium is radioactive. Francium is radioactive with a T-half of 21 days. Its half-life time is very less, it is only 21 days with a T-half of 21 days, and hence its properties cannot be studied, and hence its properties cannot be studied. Its properties cannot be studied. Okay. Can I remove this electronic configuration? So we are aware of the Aufbau principles, how we fill the electrons. According to that, you can fill these electronic configurations. Whatever electronic configurations we have written till now. If you want, you can still add. We first begin with 1s, then comes 2s. So this is the filling levels. Right, these are the filling levels. So I begin with 1s, then comes 2s. After 2s should be 2p, and then should be 3s, 3p, 4s. After 4s should be 3d, 4p, 5s. After 5s should be 4d, 5p, 6s. But this is difficult to understand. We have a simple logic for this. You need not bother about this. It is a well-known logic. What is that logic? Simply whenever you write SPDF, we begin with S. Whenever you write the electronic configuration, we start with S. The next one will also be S. First you start S, then you have written S. Then you get PS, then you get PS, DPS, DPS, FDPS, FDPS. So that is how we remember the electronic configuration. Whatever you are writing in the same, you are also writing it here. So I begin with S, then is again S, then is PS, later PS, then comes DPS, DPS, FDPS. So whatever electronic configuration we have written, suppose if I take lithium, I start it as 1s2, 2s1. I go for sodium, 1s2, 2s2, 2p6. So 2s2 is completed, then 2p6 and 3s1. So I begin with 1s, then comes 2s, then comes PS, PS, DPS, DPS, FDPS, FDPS. Okay. If you want, you can just look at cesium or francium. What is electronic configuration of cesium or francium? You started with S, then again another S. Then it was like PS, PS, DPS, DPS, and for francium, F is also there, FDPS. You can just note it down. You can just note it down, because this will remain as a basic for you. This you can apply for any electronic configuration that you write. you can just go through cesium or francium, because if you go through francium, you will also get that F. Finished? Okay, let us take oxidation state. Oxidation state. All these elements are stable in +1 oxidation state. All these elements are stable in +1 oxidation state. In rare cases, they acquire -1 oxidation state. In rare cases, they acquire -1 oxidation state. For example, in complexes, in complexes with crown ethers, example 18 crown 6, I am just giving you the 18 crown 6. Metal is present inside. This metal can also acquire a negative charge. That depends on how many crowns it is combining with, which crown it is combining with. Suppose if I take a crown ether, I take both sodium as well as say potassium. I have taken sodium as well as potassium. I am reacting this sodium as well as potassium with a crown, 18 crown 6. So whenever I am reacting it with sodium potassium with a 18 crown 6, one metal will enter inside. Whatever metal that is entering inside, that will carry say a positive charge. It is losing an electron. That electron will be taken up by another metal. So if at all I am taking only one metal and one microcycle, that one metal will enter into the microcycle, there is absolutely no problem. Whatever electron that comes out, that electron will be solvated. Okay, I am choosing microcycle. For this microcycle I have added say sodium. Sodium will be entering inside, that will form a complex. Electron will come out, that electron gets solvated. That electron is getting solvated if I take only one metal. Suppose if I take a second metal also, then that electron whichever is coming out, suppose if I am taking M and M prime, I am taking two different metals, sodium and potassium or potassium and cesium. So whichever metal is entering inside, that is giving away an electron, that electron will be taken up by second metal. Once this is taking this electron, it will become M minus. One is M plus, but the another one is becoming M minus. So that will acquire a negative charge, and all such metals will end with ide, sodide or C-side, potasside, etc. Rubicide and so on. Okay, so got the point. If it is just 1:1, then that metal does not acquire a negative charge, but if it is 2:1 and if it is a different metal, one metal will enter into a microcycle, the another metal will be taking up the electron given by this metal. The second metal will become negatively charged. This is very rare, because whenever we say 1A group elements, we always find them in +1 oxidation state only, but there is some rare condition also. You can note down that point. When two different 1A group metals combine with a macrocycle, combine with a macrocycle, combine with a macrocycle, one loses electron to become a cation, one loses an electron to become a cation, while the other gains that electron to become anion. Example, you can write down sodide, potasside, rubicide, C-side, etc. Sodide, potasside, rubicide, C-side, etc. Suppose there is a question, how many chelate rings are present in this? What is the size of each chelate ring? Because chelation is also there for you. And once a metal is entering into an 18 crown 6, how many chelate rings are present? You can count 1, 2, 3, 4, 5, 6. Altogether there are 6 chelating rings. What is the size of each chelating ring? The size of each chelating ring is 1, 2, 3, 4 and 5. So this is one chelating ring. And the size of each chelating ring is 5. It is a 5-membered chelating ring. Altogether there are 6 such rings. So whenever 1A group element or a 2A group element enters into a macrocycle, it gains a lot of stability. That higher stability is due to the formation of chelating rings. More the number of chelating rings, greater is the stability. 5-membered chelating ring is always stable. Finished? So we will directly enter into the trends. All these trends are very simple, it will complete at a very faster rate, but what I request you is, you just take 3 different pages. Just take 3 different pages. In the first page, suppose if I am writing a trend, I will just write the trend, atomic radius or ionic radius, whether it is decreasing or whether it is increasing, I will just give you in a table. You take down all those trends in one page. In the second page, you just make a separate table. You can do it for yourself. Suppose I say atomic radius. How is the atomic radius increasing? Write down the full sequence. This you can do it for yourself. Every time I will not be writing the sequence, simply I will use cone diagrams. I will just use cone diagrams. What are these cone diagrams? Simply if I put it like a cone, it is tapering means it is less, broadening means it is more. So suppose if I say atomic radius from lithium to cesium, what is happening to atomic radius? It is increasing. Or suppose if I put it this way, decreasing. So just I will say either increasing or decreasing. Later on you can just fill up this table, the trend. And you have to remember this trend definitely, because the questions mostly appear from this. Okay. So begin with physical properties. We will start taking down the trends. Physical properties. What to do on the third page? I said 3 pages. First page is the table that I give, second page is the table you will be taking, third page is some explanation, why it is happening or why it is not happening. It is just for your convenience. Those are convenient you can take, or else you can follow your own method. This will be a lengthy table, okay, but every time I will be just taking a different property. Okay, write down the first property. Atomic radius. Any explanation which is needed for this, I will be just writing it here. First property, atomic radius. What is this atomic radius? In a group, every time a new shell is being added up. Okay, so before explaining this atomic radius, you can just note a few points. I'll just explain those points. You can note it on the third page that I told you, not first and second. First is for this table, second is for your table, third is any extra point that I will be telling. Okay. Whenever I choose a periodic table, which element is the beginning of the any period? I choose second period. Which is the beginning element? Lithium. I choose third period, fourth, fifth, sixth, seventh. Every element of any period begins with 1A group elements only. Let it be lithium, sodium, potassium, rubidium, cesium or francium. So these are called as the beginning elements. Since they are the beginning elements, every time a new shell is being added up in these elements. As a new shell is being added up, its atomic size will be the largest. Okay? As a new shell is being added up, its atomic size will be the largest. So you can just write down that point, then you can write down this trend. 1A group elements, 1A group elements are the beginning elements of every period. 1A group elements are 1A group elements are the beginning elements of every period. So in every period, the first element begins with 1A element only. Therefore, their atomic radius will be the highest. Their atomic radius will be the highest for any chosen period. For any chosen period. So whichever period that I take, that will be having the highest atomic size. Okay. Now we are not going in the periods, we want comparison within the groups. So in the groups, what will happen? Every shell is being added up, therefore atomic radius increases down the group. Simple. Atomic radius increases down the group. That is first trend. Atomic radius increases down the group. Second table you can write it later, but just you make out this table. You need not put it very large, you can just put thin. Don't waste lot of page. Okay. Ionic radius, because I am saying a very diagrammatic representations, all that is not needed, simple cone. Ionic radius will simply follow atomic radius. Ionic radius will simply follow atomic radius. So not much explanation, all these basics are known to us, just we have to put it in a table. What will happen to atomic volume? Volume also increase because in every period a new shell is being added up, volume is also increasing. Therefore down the group, as atomic radius increases, ionic radius increases, atomic volume also increase. The fourth property, I'll just write it here. What will happen to density? Fourth one is density. Atomic volume is increasing, what should happen to density? Density increases, decreases. Density is mass per volume. Volume is increasing, density increases. You are only considering volume, but what is happening to mass? Mass is also increasing. In every period, the first element, you are not only adding up electrons, you are also adding protons and neutrons. So what will happen to mass? Mass also increases. So mass is increasing, volume is also increasing, but the increase in mass is high, therefore density will increase. Density increases. Don't only consider atomic volume, mass is also increasing. Okay? Since mass increases to a greater extent, density increases down the group. Remember that point. Density does not decrease, density will increase. So this is one common mistake that we make. Please be careful with density. Remaining things are anyway easy. Density increases because atomic volume increases, but also mass increases. Mass increases to a greater extent. But having said this, we just put a star mark. This is an expected trend only. It is an expected trend only. Okay. For density, the correct trend is this is the trend. Though I have given it as increasing, but there is a small anomaly. You just write down separately. Why potassium is coming before sodium? The simple reason is, starting from lithium to sodium, sodium to potassium, atomic volume is increasing. But from sodium to potassium, the atomic volume suddenly increases. It increases to a greater extent. From sodium to potassium, the atomic volume increases to a greater extent. So suddenly volume has increased. Mass is also increasing, but volume increases more. Since volume increases more, suddenly potassium density drops. So potassium does not come after sodium, it comes before sodium. Okay? So this is a very important trend. You can write down that explanation also. First write down that exception. Lithium, not sodium but potassium. Lithium, potassium, sodium, rubidium and cesium. Write down a point. From sodium to potassium, from sodium to potassium, there is a sudden increase. There is a sudden increase or a large increase in the atomic volume. There is a large increase in the atomic volume, and therefore the density of potassium is less than sodium. Okay, so that is one anomaly you have to remember. Remaining things are just easy. Density increases with a small exception. Then you write specific heat. Specific heat decreases. Heat of atomization also decrease. Specific heat decreases, heat of atomization decrease. Specific heat completed. The most important one, ionization enthalpy. What happens to ionization enthalpy? Decreases. As a new shell is being added up, it becomes very easy for me to remove a loosely bound electron. What is this ionization enthalpy? Electronegativity, all these things I have explained in the periodic table basics. Okay? So ionization energy is energy required to remove a most loosely bound electron, and as a new shell is being added up, I can very easily remove an electron, hence ionization energy will drop. So what does it mean? Suppose ionization energy is dropping means, if this is lithium, sodium, potassium, rubidium and cesium, just say, it is very easy for me to remove an electron as I go down the group. For cesium, I can very easily remove an electron. So when I am able to remove an electron very easily, what is the meaning of it? What is happening to the metallic nature? What is happening to the metallic nature? Metallic nature is increasing. This is a metal which is readily losing its electron. So once it is readily losing its electron, that metal is becoming positively charged, yes or no? It is losing an electron, it is becoming positively charged. Whatever electron that is being lost, there is an electrostatic force of attraction between the lost metal and that electron. Okay? So suppose if I am giving you a metal, it has lost an electron, it has become positively charged. Now this positively charged electron, positively charged metal will attract the negatively charged electron. There is a electrostatic force of attraction, that we call it as metallic bond. It is called as metallic bond. So metallic nature is slowly increasing. Why the metallic nature is increasing? Because as I come down the group, the metal is easily losing an electron and it is establishing an electrostatic force of attraction, which is called as a metallic bond. So that metallic nature is increasing down the group. Okay? You can just add that point. Down the group, as the size increase, down the group as the size increase, comma, ionization energy decrease, ionization energy or ionization enthalpy decrease, ionization energy decrease. Next, metallic nature increases, metallic nature increases, metallic nature increases. Okay? Now just listen one more point here. Suppose if I am putting a simple light, you call it as a photoelectric effect. I am putting a light, even in the presence of that light or the photons are coming and hitting the metal, it will lose away that electron. That loosely bound it is. Okay? So photoelectric effect can be found for those metals present in 1A group element or 1A group, right? What do you call it as? Photoelectric effect. What is photoelectric effect? Whenever a photon is hitting, that is present in the light area, whenever that photon is hitting, these elements are readily losing their electrons. They are ready to lose their electrons, so loosely bound it is. Such an effect is called as photoelectric effect. For other metals, only a simple light does not give away those electrons, but these are so easily removed, they simply give away that electron, and such an effect is called as photoelectric effect. Photoelectric effect can be found for the metals in 1A group elements. Photoelectric effect can be found for the metals in 1A group elements. Why potassium and cesium are used in solar cells? This is the reason, because they are ready to lose away that electrons. Okay? Add a statement. Potassium and cesium are used in solar cells. Potassium and cesium are used in solar cells. So what is happening to metallic nature? Metallic nature is increasing. Metallic bond strength. What is happening to metallic bond strength? Metallic nature is increasing, metallic bond strength. Increase or decrease? Suppose this is one metal, second and third. Just I am taking three metals. Okay? These three metals are losing their electrons. This has lost an electron. This has lost an electron. This has also lost an electron. Positively charged, positively charged, positively charged. What is the charge on each metal? +1. So the +1 charge is distributed on a smaller size. +1 charge is distributed on a larger size. What is happening to the charge distribution? The overall charge density is decreasing. Yes or no? Here the charge density is more. On a smaller size there is one positive charge. But as I come down the group, what is happening to the density? Charge density is decreasing. That same positive charge is distributed over a larger metal. In the first case, same positive charge is distributed over a smaller metal. Now that same charge is distributed over a larger metal, can it attract the electron to a same extent? No. This is small, it can attract to a greater extent. This one is very large, the charge density is decreasing, so the attraction towards the electron decreases. Once the attraction is decreasing means metallic bond strength decreases. So remember these two, metallic nature is increasing, but metallic bond strength decreases. Why it is decreasing? Because charge density is decreasing. You can write down that explanation also. Down the group, the surface charge density decreases. Down the group, the surface charge density decreases. Therefore, the metallic bond strength decreases. The metallic bond strength decreases. Suppose metallic bond strength is decreasing, how does it affect the melting point and boiling point? Metallic bond strength is decreasing, therefore melting point decreases, boiling point decreases. Okay? You can write down. As metallic bond strength decreases, comma, cohesive forces also decrease. Cohesive forces, not adhesive forces, cohesive. Cohesive forces also decrease. Therefore, melting points and boiling points also decrease. They may give you a question, what is the order of melting point or what is the increasing order of boiling point. So you must remember, boiling point is decreasing, melting point is also decreasing. What is the reason for the decrease? Because metallic bond strength is decreasing. As metallic bond strength decreases, cohesive forces also decrease. And hence melting and boiling point decrease. Finished? Okay, now let us come to few more physical properties. What is happening to the softness? What is happening to the hardness? Right, what is happening to the softness? Softness is increasing, hardness is decreasing. So lithium is more harder, cesium is more softer. Because the metallic nature is increasing, as metallic nature increases, softness also increases. How many of you have cut sodium? At your PG level, most of you might have cut sodium. If I give you same iron piece, can you cut? Because iron is hard, but these metals are soft. All these 1A group metals are so soft that you can cut them with knife also. And within this, softness is high for cesium. All metals are soft, and within this, cesium is much more softer. Okay? Why are they soft? Because metallic bond is not very strong. They are just losing only one electron, and there is an electrostatic force of attraction between the cation and only that single electron, that which is lost. Therefore, the metallic bond strength is less. Since the metallic bond strength is less, all these metals are soft. You can even cut them with knife. Okay? You can write down that point. Softness is increasing, hardness is decreasing. So related to softness, you can just note down a point. All 1A group elements, are soft metals. All 1A group elements are soft metals. They are so soft that they can be cut even with a knife. They are so soft that they can be cut even with a knife. This is because of weak metallic bond strength. Continue. Also, when freshly cut, these metals show luster. These metals show luster. Luster means shining. They will be shining. But after some time when you see, will they shine? No, they get tarnished. After some time they get tarnished. Reason for tarnishing? They undergo oxidation. After some time they get tarnished. Reason for tarnishing is they react with air, they undergo oxidation, therefore they get tarnished. Finished? Okay, now let me ask you a small question. Why are these called as alkali metals? Because of basic nature. Any Arabian here? Because the name alkali comes from Aliquili. Aliquili means? See, from plant ashes, they have isolated some compounds. These compounds mainly contain sodium and potassium, and that they call it as Aliquili. Aliquili means plant ashes from which sodium and potassium compounds have been isolated. So based on that, we got a name as alkali metals. But we also use this alkali metal name in a different way. Suppose if I take the metal hydroxides, I dissolve in water, and these solutions will be alkaline in nature. So for this reason we call them as alkali metals. Okay, this is another reason. You can just note down that extra point also. These elements are called as alkali metals. These elements are called as alkali metals. These elements are called as alkali metals because their hydroxides give strongly alkaline solutions. Their hydroxides give strongly alkaline solutions. Continue. In Arab, Aliquili means, in Arab I have written it, Aliquili. Aliquili means the plant ashes from which sodium and potassium compounds were isolated. Okay. Now let us move to the next physical property, hydration. What is hydration? Suppose if I choose a water, this is getting hydrated. I'll just put one. Right. So this is getting hydrated. I am choosing a metal cation. That metal cation, if I put it into a solvent called as a water, that is getting hydrated. Water molecules will come and it will be surrounding the metal. Suppose if this is my metal, this is a water molecule. That water molecule is coming and surrounding it. Whenever this process is done, some energy is released, some heat is released. Higher the amount of energy released, higher is the stability. Okay. Let us come to process of hydration. When does process of hydration occur easily? This is a larger metal, this is a smaller metal, maybe I am taking it as lithium. There is a positive charge. I am taking cesium. There is only one positive charge. What is the surface charge density? In cesium, surface charge density drops. In this case, surface charge density is very high. So since the surface charge density is very high, it will attract water molecules to a greater extent. Therefore, many layers of solvent can be formed. Solvation will be very high. But when I come to cesium, the surface charge density is very less. Therefore, the process of hydration or solvation is less. Solvation is decreasing. What is happening to solvation or hydration? Hydration is decreasing. As hydration decreases, what is happening to hydration energy? Hydration energy means the energy released when hydration occurs. Whenever the metal ion is smaller, hydration is larger. As the metal ion size is increasing, the process of hydration is decreasing. It means the amount of energy released also decreases. So as hydration decreases, hydration energy decreases. In this case, more water molecules are coming close, more energy is released. In this case, less water molecules will come, less energy is released. What is happening to the size of the hydrated ion? Size of the hydrated ion, whenever the metal ion is smaller, is large. But as the size of the metal increases, hydration is less, and what is happening to the size of the hydrated ion? Less. Size of the hydrated ion is more. Size of the metal is less, but size of the hydrated ion is more. Size of the metal is more, size of the hydrated ion less. Getting the point? Here the metal is smaller, surface charge density is high, more water molecules are coming, more layers are formed, size is increasing now. The size of the hydrated ion is increasing. But in this case, the surface charge density is less. Less number of water molecules are being attracted. Therefore, the size of the hydrated ion becomes low. So down the group, what is happening to the size of the hydrated ion? Decreases, right? Hydration energy is decreasing. Size of the hydrated ion, is it increasing or decreasing? Decreases. Size is also decreasing. Lithium will have larger hydration, its size is large. But as I come to cesium, its size is low. Why? Because it is attracting less number of water molecules. Therefore, the size of the hydrated ion is less. I am not speaking about the size of the ion. Size of the hydrated ion. We are speaking about size of the hydrated ion. the most important point. What happens to the ionic mobility? Ionic mobility increases. This is the most important point. Why ionic mobility is increasing? At a very first instance, when you look at the size, you will say this is larger size, that should move slowly. But whenever it is hydrated, the size of the hydrated ion is decreasing. Therefore, the ionic mobility increases. Okay? So, the ionic mobility is increasing. Ionic mobility of what? Ionic mobility of hydrated ion. Don't get confused. Ionic mobility of hydrated ion. It is not simply your metal ion, it is a hydrated metal ion. Finished? Let us take one more property, reducing nature. Again a very important one. What happens to reducing nature or reducing property? Does the reducing property increase or decrease? Right. Try to understand ionization energy. What is happening to ionization energy? Ionization energy is decreasing. Decreasing means that electron can easily be given. Compared with lithium, cesium can give more readily. If it is able to give more readily means reducing nature increases. So, as ionization energy decreases, reducing nature increases. But this is an exception. Just put a star mark for it. There is a small exception for it. What is that exception? What is the expected trend? Reducing nature should increase. But this is what is found. Lithium is more reducing than sodium or potassium or any other metal. What is the reason for it? What is the reason for it? Moving from lithium to cesium, lithium has a higher ionization energy. So it is difficult for me to remove that electron. But whenever it is reducing, what I am now telling is, lithium is readily reducing. It is not ready to give its electron, but it is reducing more readily. How do you understand this converse statement? How do you understand that converse statement? Okay, just let us compare lithium and sodium. What is happening to the ionization energy? Ionization energy is decreasing. So, as ionization energy decreases, reducing nature should increase. Reducing nature should increase. Next. Again compare lithium and sodium. Come to hydration now. First property I have taken is ionization energy. Come to hydration. In which case hydration is high? Lithium hydration is very high because it is very, very small. Therefore, hydration is very high. Whenever hydration is very high, what is the meaning of it? What is the meaning of reduction? Meaning of reduction means, suppose if I am putting this lithium into some reaction, that is going into that reaction, it is readily giving away its electron. How readily it is giving away its electron? Because whenever it is giving away that electron, it is becoming Li plus. This Li plus is very, very small size. Okay. Let me take sodium. Sodium is also ready to give away that electron. It is forming Na plus. Ionization energy for sodium is less. Therefore, this electron is readily lost. But whenever that sodium is coming out, its size is larger. In which case hydration is high. In this case hydration is high. Hydration is high means hydration energy is also high. So, which is more stable, lithium plus or sodium plus? lithium place, whenever it is coming out, it is more stable. Lithium or sodium, once it is converting into cation, sodium is ready to convert into cation. But once it has converted into cation, which is more stable? Lithium is more stable because its hydration is more. So whenever lithium is converting into cation, its stability greatly increases because of hydration. So as hydration decreases, stability is also decreasing. So between lithium and sodium, which is less stable? Sodium is less stable. Which is more stable? Lithium is more stable. In this case, lithium ionization energy is more, it is not ready to give its electron, therefore its reducing nature should be less. But whenever it is giving away an electron, it is going into solvent. In that aqueous state, it is much more stable. So these two are countering one another, and this is dominating. Since this is dominating, lithium has a higher reducing property than sodium. Okay, you can just take down these points. Hope you got that explanation. If I just compare ionization energy, ionization energy is dropping, therefore sodium should reduce much easily. But once sodium has given away an electron, it is going into solution, its stability is becoming less. It is not stable when you compare with lithium. Lithium is smaller, once it is giving away an electron and coming into solution, it is becoming much more stable. So for this reason, lithium is ready to give away an electron. Okay? You just write down this and this. So that is self-explanatory. These two are contrasting. All these trends can be completed maximum in 10 to 15 minutes. Just write down the trend, whether it is increasing or decreasing. We can even complete it in 15 minutes, but explanation is given so that you can understand the concept. Or else within 15 minutes, atomic radius increases, ionic radius increases, atomic volume increases. We can just go on giving. Done? Okay. So these are the physical properties and the trends. You write down the explanation for this. Between lithium and sodium, comma, sodium has less ionization energy, hence it readily loses electron. But its hydration is comparatively less. And therefore its stability also decrease, whereas lithium after losing an electron, gains a greater stability, and hence has a higher reducing property, hence has a higher reducing property. Okay. So these are the physical properties and the trends. Just in 2 minutes, let us revise. Lithium, sodium, potassium, rubidium and cesium. Forget about francium because francium is a radioactive metal. And what is the half-life time? It is just 21 days. Within 21 days, it just goes half and half and half. So let us come from lithium up till cesium. Atomic radius increases. Ionic radius also follow the atomic radius, therefore it also increases. Atomic volume increases. Atomic density also increases with a small anomaly. Lithium, sodium, potassium. But what is the density? Lithium, potassium and sodium. So just remember that one anomaly. Okay. So density is also done. Specific heat decreases. Heat of atomization, everyone is not responding. Heat of atomization decreases. Metallic nature increases. Ionization energy decreases. Metallic bond strength decreases. Since metallic bond strength is decreasing, melting point and boiling point, they also decrease. Come to hydration. Hydration decreases. Hydration energy decreases. Size of the hydrated ion decreases. Ionic mobility increases. Softness increases. Hardness decreases. Melting and boiling point, I have told you, they also decrease. Come to ionization energy again. Ionization energy is decreasing. Therefore, the most important property of all these 1A group elements, that you have to write it separately. What is happening to electropositivity? Obviously, electropositivity will increase. So, as electropositivity increases, what is happening to electronegativity? Decreases. So, electropositivity increases, electronegativity decreases. That point also you have to add. Electropositivity will increase, but electronegativity, that will decrease. Okay. So all these are some physical properties that you have to simply remember. What is the trend in reducing nature? What is the expected trend? Since ionization energy is decreasing, reducing nature should increase, but there is a small anomaly. Lithium is more reducing. It is more reducing than the other metals. Okay. So we'll just take a short break and then I'll continue with the chemical properties.